Hello folks, welcome back. We are starting a new unit now after the spring break, Work and Energy. I'll be talking about what is work and what is energy and how they are related in this lecture. And I'll have one more lecture talking about the conservation of energy. And we'll be moving into more complicated questions after that. So what is work? Let's start with work. If there's a force applied to an object and the object is moving in the direction of force, parallel to the direction of force, then there's a work done by this force. So let's say we have an object with mass m and we are moving it with a force F. If the object moves along the force a distance x, let's say, we will have a work done, or distance d, let's say. And work done by this force will be F times distance. We know F is a vector. Distance is actually the displacement difference in between initial and final position. It is also a vector. And when we are multiplying two vectors, the result is scalar. So work is a scalar. But just note it's coming from the fact that two vectors are multiplied. We are going to drop the vector signs here for simplicity, and we'll be using work as F times d. Or sometimes distance could be shown as x, it will be F times x. And unit for force was Newton, MKS units as we always used, and distance was meters. The unit for work will be joules. We'll use capital J for joules. And it's equal to Newton times meter. There is another version of the units in CGS units. We don't really use it a lot, but it's ergs. This is an MKS units. If we use CGS units, the unit for work will be ergs. We won't be really using ergs. If it's given in a question, we'll be converted into joules and then do all calculations with joules. As always, we stick with the MKS units. We'll be converting the units to what we want and find the values on MKS units for simplicity. But note that there's another unit for work. This is work. For work to be a work, the force, or for the force to be doing a work, it should be moving the object in the direction of itself, parallel to its direction. If I apply a force to an object, for example, an upward direction, let's say this object is very, very heavy. No matter how I pull it upward direction, it's not moving in the direction of force I applied to it. Do I do any work? No. X is 0 or D is 0 here. Then work is equal to F times X, distance will be 0. No work done. If I can lift the object up, for example, if I'm trying to lift up a table, it's very heavy and I'm trying and cannot lift it, not doing any work. But if I can lift an object, let's say this razor I can lift up in the direction of force I applied to it, upward direction, then I am doing work. So if I can apply a smaller object, or my force is large enough to move the object in the direction of force, distance h, x or h could be for height, then I have a work done F times x. Now, let me delete these. There could be situations that we apply force. There. So this is work. Another example could be that we apply a force that has an angle with horizontal. Now, if this object moved along the horizontal to a distance, let's say d again, who is doing the work? Is there a work done? This is the directional force. But distance it moved is not along the direction of force. However, there is a component of force that is along the direction of the displacement, Fx, and it's equal to F cosine theta. And this is the work doing the job in here. This is the force doing the work in here. So work here will be x component of the force times the distance. F cosine theta is the x component times the distance will be the work done by this force. Now what happens to y component? It doesn't do any work. If I ask you the question, what is the work done by the y component of the force? It's 0. This does 0 work here. Why? Because it's not making the object move in the direction of itself. Now this shows us that a work done could be 0 or bigger than 0. So work could be bigger than 0, equal to 0, even it could be smaller than 0, which means if I am considering an object, the work done by this object is smaller than 0 means another object is doing work on this object. So it's work done by 0. Here, for example, what is the work done by M is 0, but what is the work done by F is bigger than 0. This may not make sense now, but it will make sense later on when we learn about some more information about energy and work. So this is work. Let's solve a question involving this. Force times the distance traveled along the force is equal to work. And the unit is joule in MKS units. So let's see an example. Let me read you the example. I'm not going to write it down. Find the work done by a 45 Newton force pulling a suitcase at an angle of theta is equal to 50 degrees from the horizontal for a distance 75 meters. This one is actually has a figure showing you, you'll see it when I post these, but there is a person pulling a suitcase with a force. So this is a suitcase and a person's pulling it, walking, going somewhere. And the angle in between the horizontal axis or ground is 50 degrees, and the force applied by the person is 45 Newton. Now, what is the work done on the suitcase by this person, by this force? Work done is equal to F x times distance. And the distance traveled, says the question, is 75 meters. So we have a force applied to a suitcase with an angle 50 degrees with horizontal. Pulling the suitcase 75 meters, what is the work done on the suitcase? It will be the x component again of this force that is doing the work, Fx. And the angle here will be the same, their parallel angles will be the same as the one on the floor here. So 50 degrees, Fx will be equal to F times cosine 50. And introducing here, we will have work done is equal to F cosine 50 times 75 meters. F is 45 Newton times cosine 50 degrees times 75 meters is the answer. And the results should be 2,169.4 joules. Check that to see if it's correct, and correct me if I'm wrong. So the force, the component of the force is only doing work here because the direction of motion is along x component. Y component is not doing any work. If there was a question though where we move object upward, let's say, I don't have a specific example for that, but maybe I'll put on learning catalog so we'll work on it together. I applied a force to this object, let's say, with an angle again, theta, but the object moves along the force distance. Then the force, both components of this force is doing work. The object is moving along the force, so still work is equal to F times D in here. We'll solve some more questions. and learn here. So this is what his work is. Force times the distance traveled or displacement along the force. And there is one more application of that. I'm going to tell you. We learned about graphs and how to deduce some information from graphs. We're going to do the same thing in here. It simplifies the situation a lot. So if we apply a constant force to an object and move it to a distance, we can find the work force times x. And if I draw a force versus displacement graph, let's say I have a constant force, Newton, and it displaces the object to a distance meter, and the force is constant throughout the motion. Like this, I have F, move the object to a distance X, let's say here. If you look at the area under this graph, this is a rectangle. F, one side times X will be the area. So area is equal, let me call this D actually. We call it D in the beginning. Area is equal to F times D, and we know that this is equal to work. So if we have a force versus distance graph, displacement graph, we will have the area under the graph will give us the work done by this force. Now, if the force is constant, we can directly see this, but if this is the fact, it is applicable to any situation. If we have a variant force, it will still be the same. So work done by a variable force, then, a variable force. What is this? Work done by a constant force, right? By a constant force. Area under the curve. If I have a variable force, let's say a random variant force, and displacement, and the force is varying randomly. It starts from 0 and does that. Moves the object to a distance. Still the area under this curve is equal to work. Work done by this force is equal to this area. If you can calculate it, there's a way to calculate, but we don't cover this in here. But there could be some questions we can calculate the area. We can guess the area in here, but if we have, let's say we solve a question. Let's put an example. We have a force versus distance graph. F is Newton, distance is meters. Let's say our force starts from 0, reaches to a value, and then stays at 0, and moves the object to a distance x. Let me say this is x, and this is 3x. Well, actually, let's give them values. Let's say this is 10 Newton here, or 5 Newton. We have here 2 meters and 8 meters. So if the force versus distance graph is as shown, what is the work done by this force is the question. And what I'm going to do is calculate these areas. I have a triangle here. Let me call this area 1. It's equal to always 2 sides if it's a right angle triangle. 5 times 2, multiplication of 2 sides divided by 2. So this is equal to 5. Unit will be joules because I have Newton times meters, right? So joules. This is the first part of work done on this object. And the second part will be area 2. Area 2 is equal to this distance times this, right? It's a rectangle. The distance here is 5 Newton times 2 to 8, 6 meters. So it's equal to 5 times 6, 30 joules. Again, this is Newton, this is meters. I'm just dropping the units there, but the result is joules. 5 times 6, 30 joules. And the work done is equal to addition of all these areas, so area 1 plus area 2. So it will be 5 joules plus 30 joules 35 joules. Easy as that. So we just calculate the area under, and that is the work done. If the question asks me what is the work done up to object moves to 2 meters distance, it's only this area 1. The work done in the first part is 5 joules, and then force continues to apply to the object, moves it 6 more meters, and does some more work. It's equal to 30 joules. Now, let's solve a question about this. A more complicated question. Let's see. Only thing you need to be careful about here is to know how to calculate the area under and not make any mistake in there. So let me take this question from here. Here we go. Excuse me. So we have force versus distance graph again. Force Newton, distance meters. And the variation is this, that, and this. So it's moving the objects in different sections, and we have meters. And we can put these values. Let's see. We have here 5 Newton, 10 Newton. My graph turned very good. Let me make this better looking one. There we go. We have 4 meters here. Here we have 8 meters. Have 12 meters. And then 14 meters. Okay. The force applied to an object varies as shown in figure. What is the work done on the object when the object is displaced by a distance of 4 meters? Work done, let's say call this is a work done when the object is at distance D is equal to 4 meters. This is the first part is asking. And 14 meters. And the second part is asking what is the work done? Work done when the displacement is 14 meters. When the object is displaced 14 meters. Let's call these work 1 and work 2. Work 1 and work 2. And let's look at work 1. Work done. Part A, when the object is displaced to 4 meters, will be this area under here, right? And this is a rectangle, sorry. This distance is 4 meters, and this is 10 Newton. So work done in here will be this area, work 1. And work 1, I'll put it here, is equal to 10 Newton. Let's put the units now. 10 Newton times 4 meters. 4 meters. 10 times 4, 40. 40 newtons times meters, joule. So this is work 1, while the force moves the object to a distance of 4 meters. Now let's look at overall the motion, all the motion. 40 will be still there, so work 1 is still there, and we'll calculate all the work done. Simply calculate all the area under this graph. We got it. Okay. Now we go to B. So we're going to calculate all the areas. What I would like to do, calculate all the areas, put them in here as values, and then add them up, right? So this is a triangle, half of that actually, because this is 4, this is also 4, this is also 4, and this is 5. So if I calculate the area of this little triangle, this, and these two will be the same. And the area of this little triangle is equal to 5 times 4 divided by 2, area of the triangle, right? The triangle 1 is equal to 5 times 4 divided by 2. Again, 2 right angle sides divided by 2 is the area of a triangle. I'm dividing 4 by 2 here, 5 times 2, 10 joules. Each little triangle here is worth for 10 joules. So I put here 10 joules. This is also 10 joules. 10 joules. And the same. This last little one though is not 10 joules because it's smaller. We have 12 to 40 meters, so it's 2 meters in here. And this side is still 5 joules, 5 newtons, sorry. So the area of this triangle, we call this triangle 2, second type of triangle, is equal to 5 times 2 over 2. You can directly also see this. This is half of the larger triangle, 5 joules. So this area is 5 joules. So we have 40 joules here. Let's put that as well. 40 joules, 10 times 4. 10, 10, 10 is the same, 10 joules as well. And we're adding all these up to find the total work done. Let's add them. We have 40 joules on the first rectangle here. Plus we have 1, 2, 3, 4, 5 times 10, so 50 joules from there. I have to use capital J actually. Plus the little triangle in here, 5 joules. And what is the result? Is 95 joules. Please make sure you work on this yourself, calculate the area, draw the graph, and understand it. All we do is calculate the area under the curve. And this could be very nice easy question in your exams. Last thing I want to tell you today is work energy theorem. To move into that, I want to tell you what type of energies will be studied. There are many different types of energies, but the ones we'll be interested in this course is kinetic energy and potential energy. So let's define the energy first, and then we're going to find the relation between work and energy. And we're going to finish with this lecture. We're going to continue the next one for conservation of energy. So, energy. What is an energy? It's actually hard to define without relating it to work. So I'm just directly going to define the types of energy we're interested in. We're interested in here kinetic energy. We're interested in potential energy. And I'm sure you've heard about these. Maybe you studied them before. And there are many other types of energy. There's heat energy, we'll cover it later. There is nuclear energy, electrical energy, electric potential energy. We are not covering them in here. We're covering kinetic energy and potential energy. Kinetic energy is related to velocity. If an object has a velocity, it has a kinetic energy. It's the energy of the motion. If we talk about kinetic energy, it means that an object is moving. It's in motion and has a velocity. And if we had an object M, let me draw a marble for example, I kicked the marble and pushed it and gave it a velocity, and let's say it's moving with this constant velocity. It has a mass m. It's kinetic energy, what we call Ke in here, or sometimes called an energy kinetic. It's also both usable. I'll use Ke, kinetic energy, is equal to 1 over 2 mass of it times v squared. And the unit for kinetic energy is also joule, the same as the work. If we put all these units, we have kilogram, we have meters per second squared, and kilogram meters per second squared is equal to joules. And this is also equal to Newton times meter. Unit-wise, we can describe it like this, but you don't have to know that. So kinetic energy, 1 over 2 mass times velocity squared. What if the object does not have a constant velocity? It's possible. It could have an initial velocity. Let me show it to you here. You can see that good. So if the object has an initial velocity, mass m, it's called v initial, and it changes, decreases or increases, right? Possible, we learned this in kinematics. It has a final energy, it's accelerating or decelerating. Then the kinetic energy is changing. It has an initial kinetic energy. Kinetic energy initial will be 1 over 2 mv initial squared, simple as that. And it will have a final kinetic energy in here, 1 over 2 mv final squared. And kinetic energy will be changing. It could be increasing or it could be decreasing, depending on what the object is doing. So the kinetic energy of an object is the energy of the motion. If the object has a velocity, it will have a kinetic energy. Potential energy is also called gravitational potential energy. This is the energy stored in an object that has a height due to the gravitational force by Earth. If we have an object staying at a height, it's stable, it does not have a velocity, no kinetic energy. But it has a potential to gain kinetic energy. That's where the potential energy is coming from, actually. Because if we drop this object, the gravitational force will be pulling it down and giving it a velocity, so the kinetic energy will be starting to happen. It will have a zero initial velocity and the velocity will be increasing. It will have a high kinetic energy when it falls down. Now, the energy that the object has due to the gravitational force is called potential energy. And if we have, let's say this is Earth, have a distance, stand above a distance h or height h of Earth, then we have a potential energy. We have potential to fall down and gain a very large velocity that could kill us. So that's what potential energy is. Let's say my mass is m, I'm standing there, and my potential energy is defined as, we'll call it potential energy, PE. Sometimes it's called energy potential, possible, you can see that as well. Potential energy is equal to mass, gravitational acceleration, times the height of the object, and mgh. It also has the unit, of course, as joule. I just noticed that I have meter squared in here. And this will be the same when we put the units. Kilogram meter squared divided by second squared, because this is velocity squared. Let me correct that. Not important, but to be exactly correct. Here we'll have the same. So joule is Newton meters or kilogram meter squared divided by second squared. It is. So this is potential energy, and that's it. If we have an object staying on the ground and we pull it and take it up, we are doing a work actually against the gravity, right? Our force is pulling object to a height. And put the object to a height, now we give this object a potential energy. If we drop it, if it drops somehow, it will start gaining kinetic energy. Its potential energy is causing this to happen. We'll go into that more when we talk about conservation of energy. Now, how about the relation between work and energy? Let's go into that, and this will be it for this lecture. So kinetic energy 1 over 2 mv squared, it could change depending on velocity. Potential energy mg times h is the object, energy object, an object has due to gravitational force or the Earth's gravitational pull. Now I'm going to talk about work energy theorem. And I'm going to show this to you through a derivation. You don't have to know, but to show you this is the best way to go. So work energy theorem. We're going to end up finding something very simple, very useful, but we'll do some derivations. So let's start from work is equal to force times the distance. I'm going to put x in here. And before, from Newton's laws, right, Newton's second law. What was Newton's second law? Remember? Was force is equal to mass times A. So let's enter this in here and see what happens. Work is equal to mass times A times x. Now, from kinetic kinematics, 1D kinematics, we know one equation related acceleration A, right? This is acceleration here. We remind you again. We just threw an exam, but you might not remember. And this is mass, right? And we know there's a relation between acceleration, velocity, and x, distance traveled for displacement. It is v final squared is equal to v initial squared plus 2ax for accelerating objects, let's say. Now from here, I can find a value defining a times x in terms of initial and final velocities, and it will be, I'll do this slowly. I see some of you are having trouble with this. What I choose to do here again, leave this thing alone. I'll carry this v initial squared to this side, which will be coming there as minus. So I'll have v final squared minus v initial squared is equal to 2ax. And then divide each side by 2 to leave ax alone. These two will go, and I'll just carry ax to the left side. I like it better. Ax is equal to v final squared minus v initial squared over 2. Now I can enter this value in here instead of ax, and I can have an equation relating work to mass and velocities. Work will be equal to mass times v final squared minus v initial squared divided by 2. And if I write this, I can take this to here and multiply m by both. M goes inside and divide by 2. I will have 1 over 2m v final squared minus 1 over 2m v initial squared. And this is work. Now let me remind you, if an object was changing its velocity for kinetic energy, right? It has v initial, v final, kinetic energy initial, it will have kinetic energy final, right? And kinetic energy initial, 1 over 2 mv initial squared. Kinetic energy final will be 1 over 2 m v final squared. So what we got here is actually kinetic energy final minus kinetic energy initial. I'll carry this in here. So work is equal to kinetic energy final minus kinetic energy initial, actually. And this is work energy theorem. It tells us that the work done on a system is equal to change in energy. If this object is accelerated, let's say, final velocity will be larger, right? Kinetic energy final will be larger, and we'll have a work done that is positive. If the object is decelerating, the work done will be negative. Now it makes sense that work could be negative. If the object is accelerating, that means there's a force pushing it in the direction of the motion. But if it is decelerating, there is an initial velocity already, and a force is trying to stop it. When we push the brake in our cars, that's what we do actually. We're going with a velocity, and then we want to slow down and stop. So we push our car backward with our brakes and make it stop. And then our initial energy is larger than the final energy. And if you look at the energy change, final energy minus initial energy, it will give us a negative value. That's why work could be negative. Work done by the car in that case will be negative. And to summarize this, we say work done on a system or an object is equal to change in energy. It doesn't even have to be kinetic or potential. It could be both. Any type of energy. If we take an object and move to a height, when this object was on the ground, it had 0 gravitational potential energy. And when I put it to a height, I gave it an energy. I did work and has a larger than 0 potential energy now. This change in energy is also equal to work done by me. So always the change in energy, final energy minus initial energy is equal to work. To summarize again, the work energy theorem tells us that work done is equal to change in energy, both kinetic energy and potential energy. So if we know, let me give a very simple example here, just a discussion. logical examples. So we have an object like in here. It has an initial velocity v0, let's say, and final velocity v. And I'm asking you about work done on this object. You say the object will have a final kinetic energy, initial kinetic energy, and work done on this object will be kinetic energy final minus kinetic energy initial. Velocity could be increasing, decreasing. Oh, look at that. If the velocity was constant, there's no work done. It will be 0 from here, right? If there was an object staying on the ground, it will have a potential energy 1 that is 0. And then somebody comes and takes this object to a height h, right? Now the object will have a potential energy final, potential energy initial, let's say. And is there work done? Yes. And the work done here is equal to, let me put this well here, potential energy final minus potential energy initial again. And that's it. Let me see if I have any examples of that. If not, I'll show some examples on. And don't forget again, work done could be bigger than 0, could be equal to 0, could be smaller than 0. If it's bigger than 0, that means energy, kinetic or potential energy is increasing. If it's 0, that means energy is constant. And if it's smaller than 0, that means energy is decreasing. It makes perfect sense then to have positive, negative, or 0 work done in the system. And let's see if I have any examples of this. If not, I'll find. Okay, there is a nice question here. Let me show them here. And the question is saying there is a ball standing on the ground first, and then this will have a potential energy of initial. And then somebody picks it up and takes it to a height. Now it gains some potential energy. And then she dropped it. And then the first position here, second position here, and then the object dropped back to ground again. So the third position here. So potential energy initial, potential energy 2, let's say here, medium, middle energy, and then potential energy final. What is the work done on this object by this person will be potential energy final minus potential energy initial, 0. Work done will be 0. Why? Logically also this makes sense, because you take the object up, you're doing a work against gravity, right? And then you drop it. This, let's say this work is what, 10 joule, okay? And then you leave it, and now gravity is doing work against you. And it's equal in opposite direction of the work you've done. So you've done 10 joules work, leave it down, and the gravity is doing 10 joules work, and your work is decreasing now. It's equal to minus 10 compared to your work. So the work you've done is 0. And if you think in terms of work you've done, if you take this, put it in here, you've done a work. You take this object and put it in here. If you drop it again, you've done nothing. It's in its initial position, still the same thing, and you've not done any change in the world. Makes sense that work done by you is 0. So if you pick up something, try not to drop it, because your work will be worthless. See you in class on Monday.